So when it comes to deep neural network, the neuron's computation involves weighted sum of the input or values followed by some non-linearity. So here, after taking the weighted sum, we have to apply some non-linearity. So for example, my sum is this much, so I need to activate the sum so that I am getting an outcome here, and this activation should be of nature by non-linear. So here deep neural networks go through several layers of neuron, as you know. So this is the input we are getting x0, w0, x1, w1, x2, w2, etc. Plus we are adding a bias, and now we are applying an activation function. So the advantage of adding this bias is that we can move the activation function towards left or right. So there is an offset. So this bias is nothing but an offset which is able to help us to move the activation function towards left or right. So when it comes to a deep neural network, more than 2 or 3 hidden layers are there, then we can call this network as a deep neural network. So here you have input layers, then we have hidden layers, and these are known as the neurons, and these are the weights of the synapses, and we have final activation function, and we have an output layer. The number of layers depend upon the number of input. For example, if you have 3 number of input, the hidden layer should be greater than 3 plus 1. For example, or in general, if you have n number of inputs, the hidden layer should be n plus 1. So another aspect in deep learning is the use of convolutional neural network. So in the previous case, we could see that all the layers in this network are connected to each other, right? Each node is connected to other nodes. So we call it as fully connected network. Okay. So deep neural network is a fully connected neural network, but when we come to convolutional network, a few layers are convolution layers followed by fully connected network. So that is the difference between normal DNN and convolutional neural network. In convolutional neural network, you have a set of convolutional layers where we are taking the convolution of an image with respect to a mask. Okay. So here you can see that I am taking a 28 by 28 number image. So I am going for a convolution with a padding of 1 with a kernel size of 3 by 3. So I am getting, so 32 by 32 I am taking. So it is going to 28 by 28. Then again doing a max pooling. Pooling I will explain in the upcoming slides. That means we are reducing the receptive field size from 28 to 14. Then again we are going for convolution, and finally we are going with the fully connected network for classification. So this is the structure of a convolutional neural network. So there are a lot of popular DNNs. The first one is fully connected neural network. So here you can see that the feed forward or MLP layer we call it as. And second one is the convolutional neural network. There will be feed forward and sparsely connected or weight sharing happens. And there is recurrent neural network and long short-term memory. So fully connected network we can use for classification purpose. Here there won't be any convolution, simply we are giving it to the neural network for training. And in the convolutional neural network, in addition to the fully connected network, we have a few set of convolution layers. And the recurrent neural network, we have feedback from previous stage to the next present stage. So this is mainly used for video kind of processing, because we are having video, different frames are there. It's a time series data. So for that we have to go for video kind of data, we have to go for recurrent neural network. And for long short-term memory, when you go for signal processing application or time series data, you have to go for long short-term memory. So next is training and inference. So machine learning algorithms such as DNN, how to learn their task. So the learning phase is called training, and involves determining the values of the weights and bias of the network. So generally, what do you mean by training? Say for example, I am taking a set of vehicle images. I am giving it to the network for training. So what do you mean by training? So when it passes through the network, it should identify what kind of image it is. So for that particular image, it should generate a weight and bias. Okay. If the weight and bias are finalized, you can save it for later usage. So that once you run the model and after training you save the model, so that weight and bias will be final. So when you take another image for testing, it will give the result. So here the training process or learning process is nothing but it involves determining the values of weight and bias of the network. So training is nothing but we are going to find the values of weight and bias. So there are three set of learning process. First one is supervised learning. Training set is labeled. So for example, I am giving a cat image and dog image for training. I took cat image into one folder and named the folder as cat. In dog image I take another folder, I will make it as dog. So there I am giving a label. So that's why the name supervised learning. But in case of unsupervised learning, there is no training label. I am simply giving you a set of dog and cat image. I am asking you to train. So in that case, the algorithm look at the image and see what is the unique portions in the image present. So based on that, it will cluster the data into different categories. Here there is no label because it is need to find what is the unique point in that image, and it is going to see whether this unique point is available in other images. So based on that, it will do a clustering and that will provide a result. This is known as unsupervised learning. And third one is reinforcement learning. One of the best examples is a Google car or unmanned vehicle. So there it is a reinforced learning. That means we are developing an algorithm. Let's say for example for a Google car, the car is moving. If there is any obstacle in front of the car, it will identify. So that identification is the reward from the operation. So here we need to maximize the reward. So my camera in the car will get all the surrounding details. Then the algorithm process the surrounding and it will tell whether the road is free to move. So the outcome I am getting from outside world or environment. So there, from that information from the environment, I am making my or modifying my algorithm. So there the outcome is maximized. Okay, so the maximizing the reward. Reward means the outcome we are getting from the environment. So these are the three kind of learning process available. So after learning, running with the learned weights is known as inference. So let's say for example you are developing a methodology for image classification. You take a two set of image, you train the network. So now your training is over. Your machine is ready. Now we need to test it whether it is giving the correct result or not. So for that you have to test it with some unknown images. These images should not be included in the training set. So this is known as inference. Okay. So for example here if you consider we are taking a large amount of data for training. After training we identify it as human face. So now I am taking some other data or I am taking some images by my own camera for different people and I am giving it to the network. It should identify it as a human face. So this is what we call inference. So there are different data sets are available. So the three components that enable the breakthrough of deep learning nowadays are the computational power. So we know that in the ancient days we don't have much devices for this operation, but nowadays we have GPUs, TPUs, parallel processing architectures are available. That's why we are again using this kind of algorithms. And then parallel processing, then availability of labeled data sets. As you know, nowadays there are a lot of data sets are available in Kaggle or in Mendeley or in any other challenge data sets are available. So some of the data set samples are shown here. NAAC for digit classification, CIFAR 10 for 10 simple examples I already shown. Then ImageNet is a big data set. It contains most of the general images and most of the pre-trained networks like ResNet, AlexNet, all of them are trained on ImageNet data set. And then Pascal BOC for object detection, MS Coco for detection, segmentation and recognition. Then YouTube dataset for 8 million videos are available, so for video processing. And Google Audio Set, 2 million sound clips for audio processing are available. So these are some of the popular datasets for image classification or signal classification. So here we can see that some of the sample images. The first one is NAAC dataset. This is for handwritten digits with a size of 28 by 28 by 1. It is black and white, or sorry, grayscale pixels. And it's having a class of 10 classes from 0 to 9. And here you can see that there are 16,000 separate images for training and 10,000 images for testing. So it's a huge data set. Similarly for CIFAR, it is developed in 2009. It is color image, so 32 by 32 by 3 RGB pixel images are available. And there are 10 mutually exclusive classes are there. 50,000 for training and 10,000 for testing. So let's see ImageNet dataset. So here in image data set, we have large scale image data set around 256 by 256 by 3000 classes are available. For example, it contains 120 different breeds of dogs images are available, and 1.3 million training images, and 1 lakh testing images, and 50,000 validation images. So here we have 1.3 million images are available for ImageNet data set. That's why most of the pre-trained networks are using ImageNet for training. So ImageNet large scale visual recognition challenge ILSCRC, it is happening in every year. So the accuracy of the classification is reported based on top 1 or top 5 error. Now we are going to see how we are going to train the neural network. So let's say, for example, there is 2 conditions. First one, you are studying in a class. In order to pass the class, you have to attend minimum of 5 classes per week. Okay. Similarly, you have to do your project for 3 hours. So this is a minimum requirement. So some fellows are doing 2 hours of project and some of people are attending only 3 hours of class. Definitely they may fail. Okay. So let's say, for example, okay, in other words, I will explain in another way. Okay, so you have 2 images. One is cat image and one is dog image. So you are feeding it to the neural network. So how it identifies it is a cat or a dog? How it will identify? It is based on the probability, right? So if it is, I am giving a cat image, it should give the cat value as probability as 1. But 1 should not happen always in actual practice. It may be 0.99 or 98 or above 90%. Okay. So this should happen only when the network learns properly. So when I am giving an image to the network and it is giving a value of 0.2 means it is not a cat, but actually it is a cat. But how I tell my network it is a cat? There should be some function to express that. So that function is known as the loss function. So in neural network, so here I am giving an example data set x comma y, where I is varying from 1 to n, where xi is the image and ya is the label. So when I am giving an input of cat, I am representing that it is a cat. So the value for cat will be 1. So when I propagate the image through the network, it will give a probability that should be approximately 1. Then only I can say that this will be cat. If it is 0.2, what happens? That is not cat. So you will stop the training? No. You have to make sure that go back and change your weights, again forward, see the value, maybe sometime it is 0.4, that is not correct. Again go back and adjust the weight, again forward, until you get approximately value 1. So this is what we call the back propagation, forward backward propagation. So here the main fellow is the loss function. So here we are finding the loss in terms of the label and the predicted value. So this loss function is nothing but the predicted value here. Li of f of xi comma w is nothing but the predicted value, and the ya is the original label. So the difference will be taken, and we are taking that as the loss function, and this loss function will be propagated back through the network, and we will reduce the loss function from the weight, and again we will forward propagate. So there will be there are more loss functions are available. Here I am representing 2 loss functions, multiclass SVM loss and softmax, and we will see the softmax classifier now. So let us see. This is the expression for the probability for the softmax classifier, where P of y is equal to k given x is equal to xi, which is equal to e raised to sk by summation j e raised to sj, where s is nothing but the predicted value, and we want to maximize the locally likelihood, or alternatively we want to minimize the negative log likelihood for correct class. So mathematical idea behind the softmax classifier is we need to find out the log likelihood and minimize the negative log likelihood. That means find out minus log of this expression. Okay, so this is the idea. I will show with an example. So let us see. So here I am giving an unnormalized log probabilities of 3.2, 5.1 and minus 1.7. So these are corresponding to cat, car and frog. But I am giving a cat image here, so definitely it will be a cat. So it should predict it at the output, it should be a cat. So now we will see how it happens. So first, according to this expression, this will be my SK, nothing but this one, that is the predicted value. So I get the predicted value and I am taking the exponential of this, e raised to sk. E raised to sk is 24.5, 164.18. Now I need to normalize. Normalizing means add all the value and divide it with e raised to sk. So when we normalize using this expression, we are getting 0.13, 0.87, 0.00. Now I need to take the minus log of this likelihood function. So when I take minus log, it is getting 0.89. This is correspond to the cat. So this is how mathematically it identifies which object is belonging to which category. Understood? So where this is the SK value or the predicted value. So here we are getting a predicted value of 3.2. That's why we are getting this as 0.89. So next is optimization through gradient descent. So we want to reduce our loss to reach minimum. So how can we reduce the loss? So we need to find the derivative of this loss at the current point numerically. Say for example, when I am finding the loss function, so I can find the derivative of the loss function as d of fx by dx, which is equal to limit h tends to 0, f of x plus h minus f of x by h. We already see in the +2 class. So we can use the same here. Here assume that in the first case, when you simply run the code on the first flow, in the first iteration, you are having this much weights. Okay. Then you are adding a small bias of 0.001. Then you are getting another weight, right? So based on this first weight, your loss function will be 1.25347. And second case, your loss function is 1.25322. So you need to find out the gradient, that means the change in value. So that is find out using this expression. So here h is nothing but 0.001 and the difference is 1.25322 minus 1.25347 divided by 0.0001, that is minus 2.5. So here we got the gradient minus 2.5. So this is the loss function corresponding to the first iteration. So we need to take that value and reduce it from the initial weight function. Then you iterate again. Similarly, you have to find the gradient. Do it again. So this process repeats until your detected value probability will be matching with the original one. So this is the training process. So but here there is a lot of work because we need to find the current weight. You need to add the h value or bias value to the function. Then you have to take the difference between these two and divide with this value. So it is very tedious task. So instead of this, we are going for analytical gradient. Analytical gradient means we are going for back propagation. So we can use back propagation to find analytic derivative. So let us go for a simple example. Here I can show that there is a function f of x comma y comma z which is equal to x plus y into z. Okay. So this is that, and let's build a computational graph over here. So for example, x is adding with y at this node, so it is x plus y, and at this node it is z into x plus y, and finally we are getting an output f. Okay. Now we can say that q is nothing but x plus y. F is q into z. Okay. Then dou q by dou x 1. Dou q by dou y 1. Dou f by dou q z. Dou f by dou z q. So this is the analytical methodology. So we are taking the derivative in each branch. So now we will see one example. So here we can use the chain rule. That means dou f by dou y I am having X as my input and Y as my label. I am doing this forward propagation. I am getting loss as F. Now I need to find the gradient of the loss and propagate it back. Okay, I need to find the loss in terms of X and Y. Okay, so now using chain rule, I can write dou F by dou Y is equal to dou F by dou Q into dou Q by dou Y. Okay, similarly for the other fellow. So now we can see with an example. Let us assume we have some current values in our network like X is equal to -2, Y is equal to 5 and Z is equal to -4. So let's see for example. So X -2, Y 5, Z -4. So what will be Q? 3. -3 into 4, -4 into 3, 12. So what will be F? F will be -12. So now we will first run the inference through the network and now find the derivative of the output to each input. So here we are taking dou F by dou F as 1 because your final probability is 1. So your derivative you assume that it should be 1. Now what is dou F by dou Z? Q. What is the value of Q? 3. Next, dou F by dou Q. Z. What is the value? -4. Next, what about dou F by dou Y? Dou F by dou Q into dou Q by dou Y. That is -4 into 1. -4. The other value. Dou F by dou X. Dou F by dou Q into dou F by dou X. That is -4 into 1. -4. So initially your weights are -2, 5 and -4. Now after the first iteration or first back propagation, you can see that your weight changes to -4, -4 and 3. So this is how the propagation happens. Again you have to move forward, backward, and until the error will be 0 you have to do this process. So this is the idea of back propagation. So another example is there. So here you can see I am going to implement the expression f of x comma w as 1 by 1 plus e raised to minus w0 x0 plus w1 x1 plus w2. So I can draw it as a graph w0 x0 into a. This will be a. w1 x1 is equal to b. C is a plus b. w2 into plus a plus c plus w2. This will be d into -1. This fall into -1, which will be k. Then exponential of that will be g. Then 1 plus this expression is h, and total 1 by this expression will be 1 by x. Okay. Now I can find the same expression dou f by dou f is equal to 1. Now dou f by this will be 1 by x, right? What is the expression for 1 by x? -1 by x square. So dou f by dou h will be 1 by minus h square. Then next dou f c plus x, that is equal to 1. That means you have dou f by dou g, which is also same minus 1 by h square. Similarly, you have d of f of e raised to x, that is e raised to x itself. So you can write it as dou f by dou k as e raised to k into minus 1 by h square. And next is d of f ax, which is equal to a. A is what? Dou f by dou d. Then dou f by dou x of x plus y, which is equal to 1. You can substitute this value, that is dou f by dou a is equal to 1 by h square ek, because there will be a minus multiplication by -1. So minus 1 by h square become plus h1 by 1 by h square. Okay. So this process repeats, and finally you are getting your expression for all the nodes. So this is the mathematical expression for one forward propagation and backward propagation. Now we can take an example and substitute. So here you put w0 as 2, x0 as -1, w1 as -3, and x1 as -2. So w2 as -3. A will be sum of this. So into multiply w0 x0 -2. This will be -3 into -2 plus 6. This will be -2 plus 6, 4. This will be -3 plus 4, 1. Okay, this expression is nothing but W0 x0 plus W1 x1 plus W2. What is this sum? W0 plus W0 x0 plus W1 x1 4 plus 3 minus 3 1. Okay, now it will be multiplied with the minus 1. So minus 1. So exponential of minus 1 e raised to minus 1, that is 0.37. 1 plus 0.37 1.37. Then 1 by 1.37 it is 0.73. Now the value is 0.73. It is not correct. It should reach above 90. And only we can say that it is belonging to that category. So we have to put it back. So here we need to find out 1 by h square e raised to k, which is equal to 0.2, and k is equal to minus 1, we already see, and h is equal to 1.37. So we can find out the derivative. Dou f by dou 1, w1 as 0.4, dou f by dou x0 as 0.4, dou f by dou w0 as 0.2, minus 0.2, dou f by dou x1 as minus 0.6, dou f by dou w2 as 0.2. So here we started with the weight of 2, okay, and here we started with a weight of minus 3 and weight of minus 3, but now we come up with a weight of 0.4, minus 0.6. So you are reducing your weight, then you have to propagate again so that it will give a value which is close to the 1. So this is how the training happens in a neural network. Next is batch training. So the straightforward way to update the weight is run inference on all the training samples and update weight with average loss. Say for example you have 1000 set of data, you have to process all the 1000 data and then you take the average. But it will take a lot of time. So it is too costly. So instead of that we are going for batch of inputs. Have you heard about batch size in deep learning? Batch size. Let's say for example you have 1000 image or 1000 data set. You can split it into 50 batch size. 50 batch size such 20 batches will be there. So you can process the batches one by one, or if you have a GPU or parallel processing system, you can process it parallel. So that it will make faster the system. So select a batch size that is n sample subset of entire training set. Then calculate the average loss for each batch of the sample. Then back propagate and update the weights. So a run through the full training set is called epochs. There are 3 parameters in deep learning: epoch, iteration, and batch size. Epoch means a run through the full training set is called epoch. Say for example you have 1000 data set. So all the 1000 data set processed one time backward and forward, we can call it as one epoch. And I am dividing this data of 50 batches. So you get such 20 batches. So in order to complete one epoch, you need to do 20 iterations with the batch size of 50. So iteration into batch size gives you the epoch. So another option to reduce the training time is called transfer learning. So in transfer learning, let's say for example, you are going for a general image classification. For example, human face identification. So already pre-trained networks are there, ResNet, GoogleNet, AlexNet, all those are there. These are pre-trained networks which is trained on the ImageNet dataset. So this ImageNet dataset contains all such kind of images. So they have a particular weight and bias already saved in the network. So you can use the same weight and bias and you can simply test the image which you have taken. There is no need for learning because it's already learned. So this is known as transfer learning. That means we are transferring the knowledge when you trained using ImageNet to another domain. Okay, this is what one kind of transfer learning. So this is only applicable for general images. So then that time we can use only the weight and bias. So multiplication or addition is not doing extra. We are simply using the weights and bias and we are testing. So we are starting with a trained model and adjust to new model and data set. So that is what we call transfer learning. And next is the convolutional neural networks. So first I will give some introduction to convolutional neural network. So the first one is fully connected layers have a synapse connecting each neuron layer to every neuron in the following layer. So each layer has m by n weights. Okay. So that means here you can see that this is my input layer. Here you have hidden layers and weights are going from each node to another node and different neurons are available. So here you can see that each connection in the node is connected to other nodes. So it is known as a fully connected. So they result in huge storage and computational requirement. Why? Because most of the connections are not required. Some of them are redundant. all the time, most of the network connections are not being used. So if you use a fully connected network with all connections, it is a computational burden. So when in a digital system design or digital design, we look for minimum computation. So in that sense, we need to remove the unwanted connections. So that is the main problem of deep neural network. So that's why we are going for convolutional neural network, which relaxes the requirement for deep neural network. So this is inspired by visual cortex. The thing is that cortical neurons respond only to stimuli when it is in the receptive field. So in fully connected network, it is always active. So it always active, so we cannot switch off particular nodes. So here in convolutional neural network, it is working based on visual cortex. The advantage of our visual cortex is that it will respond only to the stimuli in the receptive field. So we thought of, the researchers thought of developing CNNs for that, or ConnNet for instead of deep neural network, and these are sparsely connected neural network with weight sharing. So for example, we have RS weight layer and fewer operations per output and significantly fewer weights. So the main operation is convolution operation. Here you can see that this is your input image. So you are taking a filter with a kernel size R by S, and then we do element wise multiplication or convolution, and we are getting the partial sum, and partial sum will be taken here, and this process repeat for the entire image, and you are getting an activation map. After the convolution operation, we can activate this convolutional map so that you are getting an activated output feature map. So we will see the examples in the upcoming slides. So one of the first CNN which is developed by Jan Mekian and Joshua Bengio in 1998 was the LeNet. It is a gradient-based learning applied to document recognition. And this is the structure of this LeNet. Here we have an input, and there are input image feature maps. Then we are sampling or downsampling by a factor of 2, and it is going for a few layers followed by fully connected layer. So in the convolutional neural network, we have convolution layers for getting the features, and this fully connected network only will be for classification. Okay, and maximum 2 fully connected network will be there before the classification layer in convolution layer. All other layers are convolutional in nature. And the next one is the breakthrough in the regime of deep neural network is ALEXNet in 2012, which is developed by Alex Krizhevsky in 2012, and he won the award for that year's challenge. And this is a simple network which is having less number of learnable parameters, and these are the ImageNet challenge winners for the last few years. In 2010, 11 shallow networks are there. In 2012, ALEXNet won. It is an 8 layer, and in ISM SPRC 13, another 8 layer network is developed. Then in 2014, VGG network with 90 layers. Then GoogleNet in 2014 with 22 layers, and in RusNet in 2015 with 152 layers. So you can see that starting from 8 layer, 19 layer, 22 and 152 layer. So these much layers are contributing to more number of computational complexity. So we cannot directly implement all these network into hardware because it is more complex and it is time consuming. So we need to develop custom networks which is having less number of layers, like 8 or 9 layers. So that is the main motive now, because we cannot implement all these large networks in our system. So next is the convolution layer. So as you know, here you can see that there is a 32 by 32 by 3 color image where 3 represents the channel RGB, and we are using a filter size of 5 by 5 by 3 filter, where this 5 by 5 represents the kernel size and 3 represents the number of filters. So when you do this convolution operation on this particular image, it will give 3 such output maps. If you want to get more number of feature maps, you can go for, let's say for example, 5 by 5 by 16, that will give 16 maps. 5 by 5 by 26, you can get 26 or 32. So you can decide how many filter outputs you need. So here you can see that this is the original image and the 5 by 5 by 3 filter I am applying. So here one number means the result of taking a dot product between a filter and the small kernel with an image. Say for example, here you are having a kernel size of 5 by 5 by 3, that means 5 by 5 by 3 is 75 dimensional dot product plus a bias. So the weight will be this much, X will be the input data and V will be the bias. So this is how the convolution operation happens. And we can use multiple filters. Each filter has same depth as the input map. So you can go for a 3 by 3, so 5 by 5 by 3, or you can go for 5 by 5 by 16, 5 by 5 by 32, etc. But there can be many filters in a convolution layer. Each filter will result in another separate activation map. Let's say for example, I am having a 32 by 32 by 3 image, and I am going to do the convolution operation with 5 by 5 by 16. I will get 16 such maps. So in this operation, I am reducing the width and height of the image, and I am increasing the depth information. Okay. Let's say for example, I am taking 32 by 32 by 3 and doing 5 by 5 convolution. The convolution output will be 32 minus 5 plus 1. If I am using a stride of 1, stride means moving the mask by 1. Stride of 1 means I am moving the mask by 1. So the total feature map size will be 32 minus 32. So the total size will be, let's say for example, we are having 32 by 32 and going to do a 5 by 5 convolution. Okay. So the output size will be 32 minus the convolution size, kernel size 5 plus 1 by stride. Stride will be here, it is 1. I am only moving by 1 fellow. So 32 plus 1, 33 minus 5, 28. Okay. Now my 32 is changed into 28 by 28. So here the receptive field size is reducing. Again I am going for a max pooling operation, that means reducing the size by half. Max pooling by a factor of 2 means this will come to 14 by 40. So here the receptive field size is reducing. But in deep neural network, the receptive field size is not reducing. That is a change, difference here. So now, here you can see that I have taken 5 by 5 by 16 filters. Okay. So I am taking a 32 by 32 by 3 image, I am converting it into first 28 by 28 by 16. Then I am max pooling by 2. This is coming to 14 by 14 by 16, right? Now again I am going to go for a 5 by convolution with 32 filters. What will be the size? 14 minus 5 plus 1. That is 15 minus 5, 10 by 10 by 32. Again doing a max pooling by 2. What will be the size? 5 by 5 by 32. Because I used a 32 filter here. Now again I am doing a 5 by 5 convolution. 5 minus 5 plus 1 by 1, which is equal to 1. Using the same filter with the 32. So I am getting 1 by 1 by 32. If you look at here, when you do this convolution operation, you are starting from 32 by 32 and coming to 1 by 1. That means your height and width are reducing and your depth is changing from 3 to 32. So you are getting a depth information here. Okay. You are reducing your width and height and you are getting a depth information. And now you can convert this into a single vector of 1 by 32. So I think you heard about flattened layer. Flattened layer in CNN. This is used for converting this data into a vector of 1 by 32. This will be given to the fully connected network for classification. So this is the way by which we are doing the convolution operation. So here you can see that the same figure. I am taking 6 filtered. So 32 by 32 by 3. I am getting 6 such kind of feature maps as an outcome. So in a basic CNN, the sequence of convolution layers interprets with the activation function, and we will go like this. Here you can see that first convolution layer, so 32 by 32, 28. Again I am doing 5 by 5 with the 6, with the 10. I am getting 24 by 24 by 10, and this will go. Next is activation function. So there are a lot of activation functions in this case. So first, after the convolution operation, we need to energize the sequence. So for that, just like action potential, we are applying some activation function. And here we are applying a non-linear activation function because we need to deal with the complex data or non-linear data. And there are activation functions like sigmoid, hyperbolic tangent, rectified linear unit, leaky relevant, exponential LU. And most of the applications we are going with the rectified linear unit because it is having a positive value only when the value is greater than x is greater than 0, and other value is 0. So we can reduce the computational complexity. So we are mainly go with the ReLU in all the applications. And now the size of a CNN. So for example, how large is the output of a convolution layer? So let's say for example, I can show that I am giving a 7 by 7 by image input with a 3 by 3 filter. So my activation output will be, what is the size of the output? 7 by 7 with the 3 by 3 kernel. 7 minus 3 plus 1. 5 by 5. So you can see here. So this is my 3 by 3 kernel. This is how the operation happens. I am taking it straight with the 1. Okay. So first I done the convolution operation. I took this pixel with this pixel, multiplied with this pixel and taken the sum and replaced it here. So this is the partial sum, first partial sum. Now I moved towards right by a slight one. Taken the partial sum. Again moved once towards right. Okay, what is the size now? 7 to 5. Similarly, I am moving it by downward. Okay. By 5. So after a convolution operation of 3 by 3 with a 7 by 7 image, I am getting output activation mark of 5 by 5. So this is with a stride of 1. Stride of 1 means I am moving the mask only by once. Okay. Now next is 0 pi. If you want to get the same size of the activation mark, so input image, you don't want to reduce the receptive field size, you want to get the same. What you need to do is you need to add zeros to the outer layer of the image. So how many points you lost in the previous case? 2 pixel values. So you have to add 2 more 0 layers over here, 2 more 0 layers over here, so that it will be equal. Okay. So next is stride by 2. Previously I have used a stride by 1. Here I am going to use a stride by 2. So we can see what will be the size? 3. 3 by 3 output will be, because first case I taken the result partial sum, second I am moving by 2. So here also you can control the receptive field size. So it is 3 by 3. Previously it is 1 by 1, 5 by 5. Now it is 3 by 3. So this is how we can control the receptive field size by controlling the stride. So let's say for example, so here you have an input image of 32 by 32 by 3 with 10 filters of 5 by 5 with a stride 1, no padding. Okay. So what will be the output size? 32 by 32? 5 by 5. What will be the output size? 28 by 28. What will be the number of filters? 10. So we can see that total size is 28 by 28 by 10. So next is, how many parameters in this layer? Parameters in this layer, how many parameters? Parameters means weights. That is, each filter 5 into 5 into 3, 75 weights are there. Plus 1 bias, that is 76 parameters into such 10 fellows are there. 760. This is how we calculate the parameters. So in hardware implementation, definitely we have to tell how much is the computational complexity. Here in our CNN case, we are measuring the computational complexity in terms of the number of learnable parameters. Okay, so here you can see that this is the number of learnable parameters, 760 parameters in a single layer. Okay, similarly you can find for each layer in your network. So next is counting the size of convolution layer. Start with a two-dimensional WH input feature map. So here you can see that W and H are the height and width of the image, and R and S are the height and width of the filter weights, and E and F are the height and width of the output activation map. So apply convolution with an SR filter or weights. That means S into R times weights will be there. So each step is SR multiplications and additions. So that is MAC units. So the output feature map is of size E by F. So total of S into R into E into F max will be there. So this much multiplication and additions will be there. So this is how we calculate the computational complexity. Now there can be C input channels. This is only for one case, right? This is for a single image. But when you process a color image, you have 3 channels, right? RGB. So in that case, we have to mention the size of the input channel, that is C. So the number of weights will be R into S into C. Okay. Let's say for example, previous case, 5 by 5 by 6 or 10. So that 6 or 10 will be the C. Then the total number of max will be R into S into C into E into F. Extra C will come here. So this is how we find out the max. So if you look at here, you can see that C into R, such filters are there. N input feature maps are there. Many output feature maps are there. So there will be M number of filters, right? For each map, M number of filters are there. So your final value will be M number of filters, R and S number of kernel value, and C is the channel. So totally the whole number of multiplier and RL will be M into R into S into C into E into F. So this much MAC units will be there in the system. So let's summarize the parameter, where N is the number of input feature maps or batch size, C is the number of channels, H and W are the activations, R and S are the weights, M is the number of channels. So E and F are the height and width of the output activation. So based on that, we can find out the expression. The output feature map O of M and XY is equal to activation of biases plus input feature map into stride into filter weights. So this will be the final expression for the output feature map. It is the mathematical expression for the output feature map. So from this we will get how many operations are here. Okay. So next is additional CNN components. Okay. Okay. We will continue after the break.
Refreshments are being arranged outside, so join us for a hike.